Good morning or good afternoon, depending on where you are. We are continuing with our thermodynamics lectures. My name is Professor Duke Orata. We are continuing these lectures and we are interfacing thermodynamics, heat transfers, and fluid dynamics. So, today we want to look at the turbulent boundary layer. And when you're talking about the turbulent boundary layer, one of the first things which we need to remember is that we are dealing with very non-linear forces. When we are talking about turbulence, remember in our lectures, Introduction to Boundary Layer Theory, please I encourage you to go through some of those so that it helps you build up on what we are dealing with. We talked about laminar flow, streamline flow. And you know, streamline flow, a streamline, you can use stream functions to actually derive some expressions in relation to the behavior of that particular system. But when you're talking of turbulent flow, there is a lot of non-linearity here because we have said turbulence normally results from development in velocity gradients within the fluid flowing the system. So you have eddies and all manner of things. So you can't quite predict the behavior of some of these variables. So that if you look at a streamline flow, which you can estimate using a stream function, if we have that, it is a much more organized flow. Much more organized flow. It's a much more organized flow. For example, there's a stream and flow. As compared to turbulence, where you have this formation of eddies. So you see the streamline flow is a lot easier, it's more predictive. You can predict the behavior of the fluid very, very easily as compared to the case of turbulent flow, which you can see there in terms of that. So what does that mean? Just like you can have noise in a signal. You can have noise in a signal, so it means there must be some expected value which you will have here. You must have some expected value which you will have, your expected value. And also, in a nutshell, you want also to have an average of these fluctuating variables, because when you're dealing with turbulent flow, then you find that these flow properties vary significantly over time. It's very important to note that. For turbulent flow, the properties vary significantly with time. Vary significantly with time. So you can actually take a mean value of those particular properties. You can take a mean value of those particular properties, just like we average in terms of signals. When there's noise, find a way of averaging. You can take the average of those values, of those turbulent or nonlinear values, and normally you assume that the mean of the turbulent property, that's property which is varying so rapidly in a nonlinear manner, you can assume that mean is zero. You can assume that mean is zero. And so you can have what you expect as a value, and you can also take the mean of this properties involved in, the turbulent flow as 0. So basically, that is the framework for what we call Reynolds decomposition. It's the framework of what we call Reynolds decomposition. Now, let us try to develop boundary layer equations for this turbulent flow. Remember, when we talked about the introduction to the boundary layer equations, we talked about the Navier-Stokes equation and coupled it with the Bernoulli principle, and so we ended up with rather simple partial differential equations which had parabolic solutions as opposed to, for example, the Navier-Stokes elliptical solutions. And so let's just remind ourselves in our mind at the back of our heads that the Bernoulli remember, we said was P for pressure is equals to a constant. Always remember that. That is density. That's height. Of course, we are assuming there's no change in the datum level, so this we are always assuming is 0, and that is pressure. And so the boundary, it's turbulent. Boundary layer equation founded on that framework of the Navier-Stokes and the Bernoulli principle will give us the expressions remember we're talking of, we have taken the main values because these things are varying, so we always average values when they vary. So we're talking about main values. So we have that. X. X squared plus del 2u. So we are taking mean values, don't forget. Mean values, don't forget that. I want you to always remember at the back of your head, take this Bernoulli principle, for example. If I divide throughout by the density, I get P over rho, V squared, plus a constant, remember that 0. Already you can see similarities here. Already you can see similarity here. Think about that. Now, the second expression, now is that. The second expression is del y squared del y. So we have these two equations. We have these two equations. And so these are just a continuation of what we're dealing with, only that now we have the average values. Let's not forget that. Let us not forget that. So that if we assume using the order of magnitude analysis, so if you use order of magnitude analysis, or what we normally call a scale analysis, where of course we eliminate terms in terms of one being much greater than the other one, so that we have leading terms. We have mentioned that in our earlier lectures when we introduced the boundary layer theory, and I would encourage you very much to try and go through those lectures so that you build up the concepts in a systematic way. So if we use order of analysis, then we are going to see that we will have del x and so when we are talking of order terms of, so we will use sigma, which is the thickness of the velocity layer. Remember we talked about the velocity boundary layer, we have the thermal boundary layer, we have concentration boundary layer, but we are concentrating here on the velocity boundary layer. So in this, if we use sigma, which is the velocity boundary thickness, and just to make sure that I don't lose you, remember we had a boundary layer, don't forget. And remember, when the velocity is about 99% of the streamwise velocity, then you have that, and that is our velocity boundary layer thickness. This is there. So if we use the velocity boundary layer thickness for the transverse axis, in simple terms, the x-axis, and use the streamwise velocity length, that's for the, we use length for the streamwise velocity. We have x-axis, here we have y-axis. And we are saying for this, we will use sigma. Then for this, let's call it m, which is the streamwise velocity. And m for streamwise velocity. Now, one of the things which we know is that the thickness of the velocity boundary layer is much, much smaller, much, much less than the length of the streamwise flow. And so what does that mean? So that means that our expression now becomes V prime. Because remember, the y-axis is much smaller. Sigma is much smaller than m. So of course, we will have expressions. We'll have that expression, for example, having vanishing will be considered to be 0 in line of sigma being much less than m. And of course, the other term will be eliminated. That is, the other term is eliminated. If you look at that early equation which you had written, that term will be eliminated with the other term which you had. There will be eliminated there. Now, so this is what we have. Now, our problem here is that this particular equation does not satisfy the no-slip condition. The equation does not satisfy the no-slip condition. What does that mean? Remember, in our solution for the boundary layer equation, we had said that for the parabolic solution, involving the partial differential equation, we had that expression and I keep encouraging you, I repeat once again, please go through our lectures systematically. We talked about introduction to boundary layer theory and the other lectures which you have had. Please kindly go through them so that we are together, because we derived this particular equation there. This is the parabolic equation where when y is equals to 0, that's in the x-axis, then you will see that u over us will be equal to 0. Because y is 0, so that will be 0, or u will be equal to 0. And when y is equals to sigma, that's the thickness of the boundary layer, then we will have u over us will be sigma over sigma 0 over 2 minus half sigma over sigma power 3, and this will basically be equal to u over us is equals to 1.00. Remember, us is the stream velocity. Now, here, in other words, u will be equal to us. This is what we are interested in the slip, no slip condition. What does that mean? It simply means that for the fluid, the viscous flow of that particular fluid, the fluid flowing, we are not talking of an inviscid fluid. Remember, we have divided the flow into two sections. There's the inviscid section where the fluid flows without viscosity, and there's one where there's a viscous flow. Now, the viscous flow next to the solid wall always assumes that that velocity for that fluid is 0. And that is the no slip condition. So, like we have said, it doesn't satisfy the no slip condition. So what does that mean? It means there needs to be development of another scale other than the one which we have used, and Prandtl used model similar to that. So if you just use model, we can have a new scale which you call neta, and say that this neta is much, much less than sigma. So this is a viscous scale. And so if we use this model where neta is much, much less than the boundary layer thickness, then it means the term, the viscous term, will be there. That viscous term will be there. Let us just remind ourselves that that viscous term will be there. We had the term, and remember, we had our expression equal to density have now, of course, don't forget we're dealing with our mean values. Now, if we use this new scale where neta is much less than the boundary layer thickness, velocity boundary layer thickness, what we call we call this now a viscous scale, where, don't forget, this neta is a function of kinematic viscosity and the velocity of those properties, some property in the turbulent flow. So that really this neta can be said to be proportional to over u star. Now, remember this is kinematic viscosity. Remember that's kinematic viscosity. So that now when we use this scale, then that term will be retained. It will not vanish in scale analysis. So what does it mean? So it means now we will have that term So we have that term. Okay. And don't forget, I repeat, that is kinematic viscosity. Kinematic viscosity. So now we have the term there. So that our new expression now will be this quantity here. Let's remove this, make our lives easy. And I don't have to rewrite again. This quantity here will now be equal to 0. And now we have the new scale, that's the viscous scale, meta, much, much less than sigma. Now, you notice that we now have a problem because we have two scales. We have an inner scale and an outer scale, one involving sigma and one involving viscosity. So we have two scales. One involving viscosity, I call the inner scale, and sigma, which is the outer scale. So the challenge there is to merge those two expressions. You have two scales. So to merge those particular expressions is quite a challenge. Not intractable, but it's a challenge because you will end up with two forms. You will end up with expressions involving some power forms, leads to some power there, and you'll also have log forms. So you have to marry those two expressions. You have to marry those two expressions. Find kind of an asymptotic approach where they both merge together. And those are challenges. Those are challenges when it comes to dealing with turbulence, when it comes to dealing with turbulent flow. And that's a big challenge. That's why even in a model, even if you are to develop a turbulence model, your challenge is to get variables which are predictable, to get predictable variables. It's a challenge. So even if we have the expression which we had there, that is mu prime, v prime. That expression which we had there is the Reynolds shear stress. And this Reynolds shear stress is merely trying to convert the shear stress. Because remember, the shear stress at the wall, when the liquid is flowing near the wall, there's shear stress. The shear stress, we have talked about shear stress, remember, in our earlier derivations, and I continue repeating. Kindly go through some of those earlier lectures. We had seen that tau, which is shear stress can be written as that, where that is dynamic viscosity. And we can also have tau as rho mu, where this is kinematic viscosity. Remember those two quantities. So in Reynolds shear stress here, you are trying to develop shear stress as a velocity. So it means that you must have a factor, correlation factor, which you can multiply it with to convert it to velocity and so forth. What normally ends up being referred to as friction velocity. So in a nutshell, what are we saying? We are saying that when you're dealing with turbulent flows, they are quite unpredictable, so that you have to deal with mean values, some expected value, and the mean of those fluctuations you can assume is zero, and then develop a model, as you have seen, where we can try to account for some of these particular things. But we must acknowledge that when you're dealing with nonlinear forces, it's normally a big challenge, because getting the pattern is normally quite a challenge. But turbulent flows are very common, like we have said. Most of the laminar or streamline flows, they will continue, but as the velocity picks up, then turbulence can set it because of those changes in velocity gradients within the flow system and so forth. So turbulence remains very, very critical, and we are still working on these systems, and we'll still be coming across them as we move on. Thank you.